just random things that come to your mind when you see that image. It's big.
There's a lot of texture, structure.
Okay. Coming. Yes.
Are we sure it's not actually a cloud?
It's tough when they see the image of the cloud. So what can you say about the cloud? Yeah.
I can at least imagine that it's like very puffy, like I can feel the three-dimensional aspect of it.
I love that answer. Yeah. It's very puffy. You can feel the texture, you can feel the structure. So it's big, it's fluffy, has different colors, surprisingly for clouds. Okay. So the reason you can tell that, I'll get to it in a second, but before that, I'll show you another thing. This. Okay. What can you tell me about it?
Sort of pine tree, the way that it's structured.
Pine tree, you said?
Yeah, it reminds me like.
Huh. That's interesting. All right.
It looks like it tastes good. Maybe I'm just hungry, but
Yeah, it's like a jello a little, right? What else? What else can you say about this? Just basic physical properties, you know?
It looks like it's moisture.
Moisture, excellent. Size-wise. Say what?
Zoom so far in, who can tell?
Well, just like what would be the guess how big this thing is?
Each thing, each stem like thing is small, but maybe as a whole.
Yeah, I mean, just like, you know, like centimeters, meters, miles, universes apart. Yeah, but you know, there's some intuition we can sort of take from this image. First of all, we can see that the light is coming from the left. Would somebody disagree? Now I gave you the answer, but like, anyone have a different intuition about light? Okay. It has this what we call in graphics glints and highlights. So somebody said it looks moist. That's precisely what that sort of signifies, right? If you have a moist jello, it will look. It has what we call subsurface scattering and absorption. So the color of this object is actually given by the volume of the object. It's not a surface color like a paint. It's actually inside of those little tubes or stems. Subsurface scattering. There is something called global illumination. So there's light diffusing through the volume of this thing. So you get these subtle shading hints. And all of that stuff your brain processes automatically. You don't have to think about it. When I asked you, then you thought about it and then you gave me the answers. But you internally sort of make those calls as we go. There's also something called depth of field. Those of you who like taking pictures, macro pictures, you know this very well because you see something small and you have this defocusation effect. So this is done deliberately, and it's actually to make this structure appear smaller in this rendering. So I have a thesis for this talk. For the sake of just going faster, let's just agree with the thesis, and if you disagree, then we can discuss it in the next session. So it starts with the premise: everything we know about the world comes from or through our senses. We see the world through the senses. We understand. Therefore, our minds build a representation of the world based on perceived information through those senses. Therefore, our minds construct intuitive models of the world to process information efficiently. Therefore, to gain understanding about something new, epistemologically, it can be process, it can be data, it can be grandma's chicken soup. We should take maximum advantage of those intuitive models. So this whole slide just says, if you want to understand something new, you need to rely on your intuition. You need to somehow draw attention to things in that new thing, in that new process or data that people can connect to. Does that make sense? All right. So do something about volume rendering. So I started doing volume rendering in this context, simulating atmospheres of planets. Later on, I moved on to more dense media or volumes, just clouds, smoke, or funny running elephant in a box. All of this is simulated in real time on a single GPU, such as you can have in your laptop or PC. That was the point of the work, to simulate this process of volumetric light transport in volumes in participating media as efficiently as possible. And through that, we had to develop new models and new intuitions, new ways to process this information. I worked on rendering high quality images like this, simulating the subsurface scattering in tissues, in milk, in jello. And that mostly does work of reducing variance. So some of you know what Monte Carlo estimators are, or Monte Carlo simulation. This is all Monte Carlo work, devising efficient sampling strategies to come up with ways that you can go from this to this in the same time, thanks to render them. Having learned about volumetric light transport, I applied this to 3D printing. So we had the problem of if you want to 3D print a picture on semi-transparent plastic or marble or whatever wax, and the printer gives you really this, so sort of blurry, diffused, imprecise version of that design. How do you make it better? How do you come up with something that's sharper, that has better color fidelity? And so then I would like to sort of transfer that knowledge into the problem of visualization anywhere in science, but in case astrophysics. I won't actually be showing too many astrophysical visualizations today. I want to really talk about the substance of the problem. And then as we get to it in the second session and tomorrow, we get more spacey pictures. Rendering. Who ever heard the word rendering before? Okay. So just to formalize that, rendering is the process of transforming a mathematical description of a scene or a world into an observable result. So an image in our case. In the process of that transformation, information about reality is copied, modified, shuffled. Basically, you lose information when you render stuff. You know, take the whole spiel about the pipe and representations. We lose information about the data or when we draw it. We might add something. That's a nice feature. Add understanding, but first you have to throw something away. And in the case of volume rendering, you have to throw a lot away. It's just really vast. So to kind of draw a parallel with what you know very well and much better than I do, take this guy, Hubble, I believe. This is, I think, the Hubble Deep Field picture. And this is a picture of a single nebula, probably, that the Hubble observed. And there's something about this picture that is added during the process of the making of the image. Do you know what is added? That is not a physical observation. Yeah. So people call this the false color, right? And it's basically a way to emphasize some information or to sort of merge a variety of information into a single picture. It can be different spectral wavelengths for it. Rendering can also be seen as a process of measurement. So if I have a scene, it can be this room, or it can be a little piece of simulated yellow jelly, weird thing. You can think of the process of rendering as transforming that data into a visualization by the process of measurement. So how much light, how much radiation is coming from that object. And so I want to illustrate how the pipeline goes on a movie. So do you know Avatar? So yeah, the whole movie is pretty boring in terms of story. I mean, let's not kid ourselves. It's a children's story. However, visually, that movie is stunning, and it was a milestone in visual production. First, because the director or the production team, they had a real-time pre-visualization of what's being filmed as they were filming it. There was a rendering process running in the camera and showing a rough coarse visualization of what's going on. Yeah, they had. That's why how you can film in a virtual world, right? Like when you have to add something digital. Well, how do you explain to actors? Like, oh yeah, there's going to be like a blue human-sized cat, like grabbing your hair or something. Right? They do that in the movie. How do you transfer this to actors' behaviors? So they had that. So the movie, anyway, is a sequence of frames or images. You surely know that. So there is a single frame here. A single frame is composed of a raster, which is Latin for array, which is just to signify we have a regular grid of pixels. So here we have a single pixel. And now we want to see what's inside of that pixel. What is that little band of color actually made of? Right? In the movie, you just see a single color on that pixel. Well, here is where it gets complicated, because that pixel is actually all the light that is bouncing around the scene from everywhere, that hits a little patch of, let's say, a skin, you know, on the cheek of the character, and then bounces to the pixel, through the space of the pixel to the camera. And we have to simulate all of this. We have to actually take that into account to make, you know, a legitimate looking image. So it becomes quite a complicated problem. And the way how we can even think about the problem, there is usually a whole course on this, like it takes a semester. So I'm just trying to give you some intuition. So this here is a condensed version of the rendering equation. The equation that describes all of this light transport as it reaches that pixel. And what this basically says is we want to measure the light in the area X. So in the area that would correspond to the little window in the camera that then corresponds to the pixel in the image. Okay, so how do we get the light? Like, how do we take all of these and just throw it in there? Well, we integrate, right? Integral is basically a fancy addition or a sum, but in a continuous world. So we integrate the product of reflectance and light, or at least this is how we usually think about it. It's simpler. Yeah. So light is just all of the photons that are hitting this little patch of skin. Reflectance is somehow describing the property of how the skin reacts with light when it hits it. So how much of the light is actually reflected into the pixel at the position X prime, which is here. And the reflectance is some kind of a complicated function that eventually returns color or a spectral value. So the percentage of light that bounces from that object. Does this make sense? Or anyone or something? Yeah.
The light of it at X prime, is it like a very small? You are expanding that in a whole area?
Can you rephrase that?
The light at X prime, what is the difference between light at X prime and light at X?
Oh, right. Okay. Good question. So light at X prime is all the light that's coming from everywhere in the world. So kind of hitting that point, right? Here I have a mouse. All the light that's coming from the room is hitting every point on the mouse. And then, so that's X prime. And then at X is what I actually get through the pixel. So sort of what would land in your eye from this mouse. So nothing happened. So the interesting thing starts when you start looking at what this light is. Actually, the question that you just asked. So let's expand this a little bit. Well, here is the left side of this equation. We have the light is proportional to the integral of reflectance times light. But now you can kind of see that to get the light that's hitting this point x prime, we need to actually solve for the same equation. Right? I mean, it's light is on the left side and light is on the right side. Of course, we would call it radiance or something, but the point is here. So to solve for the light that's hitting point x prime, we have to solve the same equation. We have to again simulate the light. It's coming from somewhere, hitting something there, and then it's arriving to this position. So to get this, we substitute again the left side, and there's the whole integral again. And so we'll get multiplication with an integral of reflectance at some virtual point x double prime, which we see from this point somewhere in the world. And so it goes. So actually the rendering equation is an infinite series of integrals. And that's quite nasty. We don't know how to solve that analytically. So usually you have to solve this numerically. And
When we assume the light comes from infinity at x prime. Okay. Assuming that the light comes from infinity at x prime, such that the reflectance is 0.
Sometimes you can, but most of the time it's hitting something else, right? So let's say we have lights on the ceiling here, and then they hit. As an example, because most of the projects are hitting it, is the desk somewhere, right? So, and I'm looking at the desk. Some of the light that's reflecting towards me is coming directly from the light sources, but most of it is not. Most of it is coming from screen, from you, from the ceiling, everything around. But we have to basically account for all these different possible combinations that light can take to reach you, to reach the observer or virtual camera. It can't be at infinity. You have to account for everything that's around, and that's why the problem is doing. So it's a recursive sort of expansion of this equation. For just to give you an idea, if you have a glass of milk, or a cloud, light bounces or scatters hundreds of times in those objects. So really, every photon will just do, and eventually you see it. Camera sees it. So it's this sort of chain of events that has to happen. It's very long and complicated, and have to sort of have in the little plastic tiles that I was showing you, you get something like that too. You get hundreds scattering events that eventually form the image of the surface. That is just expensive to simulate. Any other question? So that was surfaces, by the way. This was just hard, solid objects like the mouse or room. But what happens with volumes is we have one more dimension to integrate. So that pixel actually becomes sort of extruded towards through the scene to infinity. And then the rendering equation also changes. You have to suddenly solve an integral that runs through all of this, and that integrates through the volume of this sort of virtual box, which is very narrow but long. And also there is a new term that's called transmittance. So that actually describes how much light is absorbed on the way towards the camera, on the way towards the pixel X. And we have the same problem of having to expand these things. So you have this infinite expansion of the integral. So there's volume rendering. Any questions about the
way it's drawn? I guess I'm wondering what the field of view is like. Can a light ray come at any angle as long as it passes through the plane?
Actually not, because if you think about it, it's like the pinhole camera. The model is like the first camera, which was really just a box or a room with like a little pinhole there. And so through that pinhole, you can see only a single direction wherever you stand, right? So in this case, the sort of the functional model that they use in graphics for a camera is called the frustum. So it's a pyramid which is divided into millions of tiny little pencils. Those pencils are divergent a little, so they have a width which gets wider, but you can sort of consider it just to be like a narrow tube or something. Yeah, the word pencil is used for it, but I don't know how common this is. But yeah, so normally you don't have to account for every single direction to every given pixel. Every single pixel sort of corresponds to a very narrow bundle of directions. Cool. So let's do something easier for now. Computer games. So anyone here plays computer games? Few people. Okay. I used to be a gamer and then stopped because it was just too much. Yeah, you know it, right? But this is a particularly beautiful game called Red Dead Redemption. It's not a nice game because there's two people in it. Good at you back, but again, it's a beautifully rendered game. That's what I want to discuss here. And so, why am I using a game to show the importance or relevance of volumes and volume rendering? Well, because game developers are lazy people, and if they don't have to do something, they just won't. So if you have a AAA game like this, everything that is relevant is going to be simulated in there, and therefore there will be attention put into visual. So I want to use this game as a case study for why volumes are important and sort of everywhere, really. So in this very scene, you have all this atmospheric sort of fog around the character, which gives the shot this kind of yellow vintage sheen, almost, or sepia, you could say. Here's a scene where maybe early morning, you have these, they call them God rays, or technically crepuscular rays, which are part of every beautiful landscape picture. The clouds, the weather, the snow on the mountains, the trees down there, they're all volumetric media, they're all volumes, not just hard surfaces. Characters, all these fabrics, but also especially human skin. We are walking volumes. We don't usually think about it that way, but if you shine some light through your skin, it will diffuse, and so you have to actually simulate that to get a realistic looking person. Hence, your blue kitties in Avatar. They wouldn't look right if they weren't volumetrically simulated. Fabrics as well, by the way, also fur and snow. So animals, again, they would look pretty boring if they were just simulated as hard surfaces, hard objects. So this just shows that volumes are everywhere, and we as humans look at them all the time when we see each other or when we see the nature, and also when we see the universe. And so what we don't realize is that we actually have intuition about how volumes look, how volumetric media actually appear to us, and we should use that intuition. In terms of kind of sorting volumes, what types of volumes do you have? There's many ways to do it, but you can think about it just in terms of density, like density of particles in the actual thing. So that the sparsest volumes are kind of very sparse thin gases, like interstellar medium or our atmosphere. Then you get to slightly denser stuff, so fog, clouds, vapor, smoke. And then you get to actual hard materials, to liquids, waxy looking things, also tissues, diamonds. They don't look very voluminous. They have the same light transport in them as. So basically, much of what we see is volumes, and we sort of think about them in this axis. Questions?
So in the video game, like you showed us like about the fox and others, so they colored those animals based on the natural colors, like. But if, for example, if any entity is new, we didn't see earlier, so how will you impose, for example, any universe?
Yeah, it's a good question. I mean, you're probably asking about data, right? If you're visualizing it, well, you probably have intuition about it yourself when you're working with it, but you can definitely try to use different colors to start with. Right? So when visualizing data, colors are arbitrary to the extent that there is no fundamentally right color. But of course, I mean, you had a lecture on color perception yesterday. So some colors are better than others just because, let's say, yellow things are more contrasting on blue background than on green background, because yellow and blue are further on the spectrum. So those kind of considerations are important. Okay, so what kind of interactions we have between light and volumes? So how do we actually think about light interacting with volumes? So there's three possible or three fundamentally different ways. The first of them is emission. So photon is created or radiated out from an object, let's say light or a projector or the sun. Scattering, a photon is redirected, so it changes direction after hitting a particle of the medium. And finally, the photon can be absorbed, so it's lost and its energy is converted to another form of energy, let's say. So these diagrams kind of show it. So emission, if we have light traveling in some direction and then there is something, a particle, it's emitting light, it will add into the existing light. Scattering will redirect it either outside or inside, the direction that we chosen as a reference here. And then absorption will remove some light from the existing beam or bundle that's traveling through space. In terms of visuals, what it looks like is emission just as light. So here is kind of a puff of smoke or something. There's a surface down here. You see there is no shadow because something that only emits can't actually create occlusion. Absorption only removes light. So if we have this puff, you see a very distinct shadow there. It doesn't add anything, so everything just becomes darker. If you combine emission and absorption, you get this. So there is some light, but also some of it is absorbed. This is scattering, so only redirection. In this case, there is light coming from the top, and then it's redirected by this multiple scattering process inside of the cloud or smoke. So there is also shadow. But you combine all of them together, you get something that actually looks pretty, decent, like a smoke. It casts a shadow. It has sort of illumination or shading features on the surface, so you can actually see the shape of it. And yeah, the color is sort of. So yeah, what are typically sources of these interactions? So emission, any star is equal plasma, so it mostly just emits light. But of course, there is also scattering within that volume of plasma. Absorption, typically smoke is very dark because it mostly just absorbs. It doesn't emit anything and it doesn't really scatter all that much. And then scattering itself, so clouds are an excellent example. Clouds are almost just scattering media. And so they get to be very bright and also again, you see all those features on the surface. But of course, any real medium is a combination of these three effects. We don't really glow that much. Here is maybe not a very nice scene, but it combines all these three types of interactions. So you have emission from fire, you have absorption due to smoke, and you have scattering. There is some kind of fog here. It's probably fire track, and all that light is scattering. I'll skip this. But an important thing in volumes is how light travels in them. So let's say we have a scenario where we have light starting here. Let's say it's been there and then it travels in this direction. So due to all this absorption and scattering of light in that path, in that trajectory, light is going to be lost. So basically the visibility of the volumes, which we call transmittance in technical sense, is sort of a decreasing function, and it's a negative exponential. It really is an exponential distribution. What this tells you is if you have some amount of light here, then in this distance, I'm just going to take words instead of some kind of signs here. In this distance, light will decrease by this factor, and that factor is distance times the optical density. The more optically active particles the volume has, the faster this intensity will decrease. So you get less light at the distance. And you all know this intuitively, right? If you're in a foggy city up to the morning, you see a building in distance, you can barely recognize it. And then as you come closer, it becomes more visible. So that's because of light scattering, removing the light from from the path. This is actually a very practical thing. So in measuring optical properties or chemical properties of liquids and materials, you can use light. You can sort of, if you know the chemical composition of this, but not the proportion of those particles, dissolved in this, and use this equation or this law to measure the density or the concentration of the medium. And yeah, this is called the Beer-Lambert law. Beer-Lambert is the third guy. Okay, so these were interaction types. So emission, scattering, and absorption. And then we have visibility. So how do we actually determine light's intensity changing when it travels through the medium? Then there is a question of representation. So how do we actually represent volumetric media? We have a function here of XYZ. So it's a simple three-dimensional function that returns a real number or positive real number, 0 to infinity. And you can just see that as a density of particles of that medium. In this case, I was showing you the elephant running in the box. So the way how this was represented is a three-dimensional just grid of values. Let's say in Python it would be an array, and the higher the number, the higher the density of the path. Then when you add illumination into this, you see that the elephant actually scatters more light, so it sort of comes out as a distinct object. Right. You might be familiar with this from another context. So in medical imaging, when you take a CT or MRI, what that does is actually it measures the density of the tissue depending on something. So in terms of, in the case of X-ray, you're actually measuring the X-ray absorption potential of your tissue. Regular X-ray does the same thing, but it only does one projection, a flat picture. Whereas a 3D tomograph or 3D X-ray gives you the whole three-dimensional distribution of your tissue. So you can, see if there is something growing there that shouldn't be growing there, or if there is a piece of bone inside of a fracture, something like that. So this is very useful. And these data are represented basically the same way as in the visual production context or as in the astrophysical data. So if you have a density field, let's say a nebula, or the density of the intergalactic medium, it's a 3D grid of scalar values, possibly multiple channels, depending on what you're actually studying. Any other scaling? So if you have, don't really pay attention to the units here, but if you have absorption of 5, and then 10, 15, and 30, you see that this medium, this very simple example here, becomes actually optically bigger or denser. So this is 6 times as dense as this one, and also the occlusion potential of this is going to increase. Right, so before we get to the actual rendering, so again, just a quick summary. I try to capture all these possible interactions and different ways that light interacts with volumes. Why is this relevant? Because many data in astrophysics are volumetric data, and when you're visualizing these, you essentially have to take these things into account. You don't have to, but in this talk and today, I'm going to try to convince you that this is beneficial for visualization. Yeah, any questions or anything to add here? Right, so I want to try to explain ray marching. Ray marching is kind of a generic visualization algorithm, how we're finally getting to the computational stuff. You can see there's a template for numerical integration along array. So if I'm making an image of a nebula or of a star, which is represented as a volume, I need to integrate all the light that is coming to me through the pixel, through every pixel in the image I'm generating. And I need an algorithm to do that integration numerically, and that's ray marching. What I mean by generic template, I mean that the algorithm itself is independent on what you're visualizing. It's like a black box. You just insert the particular coloring and sort of different parameters that then determine what the thing will look like, but the algorithm won't change. And again, we can take into account different ways of integrating this visual information. So we can have emission only ray marching, emission plus absorption, or all of the three interactions we talked about. And in the session after the break, I'm going to show you examples of all of these when actually applied to data. So yeah, so this is again the generic template that I meant earlier. So I want to obtain the value of something, let's say an intensity of light along a ray. How do I do that? Well, it's an integral along the ray of some function f x, where x is positioned in the point. Well, let's say we have an observer. I don't know why it's a skeleton, but it's a skeleton. And the skeleton is looking at a cloud or medium, and is looking along the ray. So this would be, as per your question earlier, this would be a single pixel in your image, and then that pixel is represented just as a ray. We know that in reality it's not just a ray, but kind of a bundle of rays. But we can just simplify it for them. So what ray marching does is literally you're just marching along this ray, at least within the volume of this object, and taking samples of it. So you're reading the optical properties of that and calculating how much light is actually traveling from every one of these points towards the observer or towards the camera. Easy peasy. So yeah, this is every one of these is a sample of the function fx, and the function fx is telling us something about light. Okay. So an example here that's actually practical, direct volume rendering. So typically most volumetric renders that you'll ever see are of this type. They account for emission and they account for absorption, and they completely ignore scattering because it's so incredibly expensive. But I'll show you an example of how to do that. So what do we have here? Okay, so this is the situation. So we have function fx. We're taking samples of it. Again, every one of these is a sample of the function fx. We can call it the illumination function. And then what you have here is a composition of several things. Some of them add light, some of them redirect light, and some of them remove light, exactly as we were talking before. Emission, absorption, scattering. So the blue ones redirect light, the red one removes light, and the yellow ones add light. So what are they? So we have, let's focus on this point here. Can you guys see on the side? So let's focus on this point here. So we have some light being emitted from of that point, let's say it's a global plasma, in that direction. So that's the E at the position X. And then we have some other light that's coming from somewhere else. It's not originating in this point, but it's coming from here. Let's say it's been emitted by some external light source, or it's been scattered multiple times within the volume, and then it's so that's L at the position X from a direction L this direction. And then this part is multiplied by what we call a phase function. I had a few slides about it, but skip them because it's kind of boring. But this is basically a directional distribution of light after a scattering event. So you can think about it as a directional probability distribution function. Simple enough. Okay, so this tells us how much light is being emitted or scattered at this point. And that's this part. What about the rest? This here is the scattering coefficient of the medium. It will translate to something like optical density. I was showing you that small clouds, the denser that gets, the denser the medium gets. The higher this is, the more light will scatter at that point. Easy enough. And then we have transmittance. So transmittance is a function of a position and a direction, or two positions. I've been showing you this Beer-Lambert law with the laser in the chemical, whatever pipette. And what that does is it computes the fraction of light that reaches the viewer from this position. So from X, in this direction, we're going to lose some light, and we'll lose it due to was going to remove light from between this point and the viewer. Absorption and scattering. Perfect. Yeah, and that's it. This is volume rendering. So this volume rendering without multiple scattering, so without the global illumination. So what about global volumes? Well, again, we have a whole course on this. So just very quickly, this here is the radiative transfer equation, transport, developed by Chandrasekhar in 1960. This was in the context of nuclear physics. So, you know, if you have a big reactor and you're trying to calculate when that thing is going to go supercritical, kind of need to know some math around it. And so they developed it's a differential equation that computes if I'm in a certain position in the volume or participating medium, how is the radiation at that point going to change in a little differential step? That's what that equation is describing. And we don't have to understand it completely, just the intuition. So if we have, again, a piece of volume in that position, what is going to be the difference of radiation? Well, again, we have absorption and we have scattering. And the scattering is actually a directional integral over the entire sphere of directions around this point, and then just pulling all the light that's coming towards that location. It's the same process as we had so far. We're also accounting for light that's coming from behind the object, which is going to get absorbed and scattered on the path towards the camera. So yeah, so this is the framework that you use to make images. There are two ways to do this. One of them are probabilistic methods, Monte Carlo methods, in other words. The other one is deterministic for finite elements. You probably know all this from the context of astrophysical simulations. An example of a Monte Carlo method would be photon mapping. We actually don't use it because you have to store the photons as you're tracing them, but it's a good sort of way to think about the process, because when we talk about path tracing, it gets easier. Anyway, so what photon mapping does, it starts from a light source and then shoots photons into the volume. And every time you have a scattering event or an absorption event, you just store the photon. You just remember where the light interacted in the volume or with the volume. Again, another one, you simulate another path. These are random walks, you know, Monte Carlo, Markov chain stuff. And you do the same thing. You do the same thing many, many times. and then eventually you end up with a distribution of light approximated by this discrete interaction events. And this is an actual sort of density of light that you can then render. How you render it with ray marching. What do you know? So you have an observer here looking in the volume along a certain direction, and then all you do is march along the direction, and then for every sampling point you just sort of add up all the photons that you find in some kind of close vicinity to that point. Photons each have directions, so that's also important for the directionality of this. And then you add them up and send them to the cap. So this is the simplest conceptual way how you can compute the actual full transport. Again, in practice, this is rarely done because you have to store all these photons. And in practice, we're talking about hundreds of millions of photons, possibly billions, and that's just too expensive. You can do it, but it doesn't scale very well. Anyway, another nice conceptual way to think about light transport is light diffusion. So what this shows you is you split the volume into little bins, and in every bin, you estimate the initial amount of energy that you receive from the light source. So kind of just a quick and dirty estimate based on the transmittance. So you see that as we progress into the volume, we keep losing light, and eventually there is going to be, most of it will be absorbed. And then what you do is you relax this information iteratively. So you basically simulate the energy exchange between the neighboring cells. So here we have a cell that's sending light to the neighboring cells, and that means we remove light from here and add it to the neighbors. But of course, we do this for every cell many, many, many times, hundreds or thousands of times. And eventually we get sort of a relaxed, resolved equilibrium distribution of light. How do we visualize that? Ray marching. Again, same thing that we already seen. Okay, any questions about it?
Other situations where you can't do this and have to do Monte Carlo?
You actually almost never do this anymore. So there used to be a time, kind of a paradigm shift. So people, before we actually copied the rendering equation from the particle physics guys, they the whole rendering just stole the master equation from the particle transfer people that invented it in the 60s and simulated it in the 70s, and then in the 80s graphics people came and were like, yeah, it is a new problem. Anyway, since we didn't have the governing equation, we were just estimating everything. And so finite element was very useful because then you can just do this like little boxes and exchange of energy and then integrate it very simply. But then again, once you get to real resolutions, real amounts of energy, pixels, and that goes up as displays go up in the resolution, you just run out of memory. And also the scaling of this process is terrible. It's like n to the power of 6 or something. Yeah, it's awful. Memory grows with the cubic, with the third power of resolution, but also then the time to resolve the equilibrium distribution grows like with the second or third power, depends on the conditions of medium. Anyway, it's bad, but it's been used to make images for decades. And then in the 80s, somebody in graphics was like, oh, there is actually a governing equation for the rendering problem. And so we just stole it. And since then we were using that. And then it turns out that the rendering equation is much easier to sample with stochastic methods. So in the last, say, 20 years, the whole visual production actually moved from pretty much doing anything else to just doing Monte Carlo. Especially in the last 10 years, there's been just like the one thing that everyone does. So used to be, if you see a Disney movie, might have been this, like in the 90s, not anymore. They just do path tracing, which I didn't actually show you. And so in the remaining 5 minutes, I want to actually show you path tracing. I had some stuff about color, but then we informed that you actually covered color. The only slide that you probably haven't covered would be, well, how do we color volumes? You know, how do you take something that's a physical quantity like a density of particles and make a color out of it? And so what we do there is called the volume transfer function. So the transfer function is just another function that takes, let's say, density of particles in the volume, let's say density of interstellar gas, and then converts it to color. And then mapping is called the transfer function, and they can look like this. So, you know, you can map density from 0 to infinity or 0 to some maximal number to this kind of color ramps. Typically, in the volume rendering context, you will have multiple such functions. For emission is usually the most important if you have something emitting, and even if you have not something emitting, then it's good to make the volume emit something, because then you can actually emphasize things in the volume that you're most interested about. So if you want to visualize the interaction between stars and the interstellar medium, well, make the stars glow and make the interstellar medium scatter and absorb. Scattering and absorption, in nature, they are spectrally dependent. So again, our tissues are the color they are because they absorb more of blue than red. Right? Yes, unlike Avatar, we actually absorb more blue. But both absorption and scattering are spectrally dependent functions. Usually we don't care. Emission, however, is really good to have RGB. So all these color maps, they are usually applied to emissive color. And then you might have multiple sources of information, which I'll show in the visualization in the second part, which where you have, let's say, two different modalities and they're squashed together in the same volume. And now what? So it's good to actually choose colors that are complementary so that you can distinguish these different components of the volume. Anyway, these are just my favorite, usually my favorite transfer functions. This is derived from the light body radiation, which we all have intuition about, turns out. To that point, this is the magma color map from Matplotlib, I think. Kind of a nice one because this is sort of the red end of the spectrum and this is towards the blue end. So anyway, it nicely discriminates those two parts. And this is actually a sunset in Santa Cruz. So this is, I just took a picture and then sampled that picture and it's a nice gradient. Turns out sunsets are another thing we have into. There's tons of work on color. I guess you've seen that yesterday. People have derived color from famous paintings, discrete color maps or continuous color maps. It's quite interesting work. So, still haven't explained path tracing, but let's take a break. Thank you.
Before we go into the break, are there any questions for Oskar? So yeah, we'll come back at 10:30. As usual, in some part of the break, not looking at the screen.
$2 off.
All right, everyone. We're gonna go ahead and online get started with the hands-on part of this. There's a reminder, there is and back. So,
Do it.
All right. So, okay, people still coming. Okay, so the practical part is going to have way fewer slides, so hopefully that's a good news. And we'll be experimenting with some software for prototypes and something more readily available, showcasing interactive global illumination of volumes. We had a little technical issue, so what I'll be showing you is more like a stop motion animation because my computer refuses to stream real-time rendering of the screen, but it will be enough. So in the first part, what I want to show you is a software polyform. I've been developing this over the past sort of 3 years as a tool to reconstruct cosmological gas distributions, so the cosmic web. I'll tell you much more about this tomorrow when kind of giving you the history of how we do this and showing you lots of visualizations made with this. What I want to show you now and give you kind of an example of how all those interactions and ways of light interacting with volume, how those come together in visualization and how you can change them and modify the different parameters to actually show different things in the. So let's see if this starts. So this here is a tool that that reconstructs the cosmic web from galaxy positions, and it's just an approximation, obviously. But here we really won't care about the method of doing that. We'll just care about this software giving us some volumetric data to play around in visualization settings, and and how to work with that. So what you're seeing here. This is a particle rendering. When I zoom in, the red particles are galaxies and the white particles are agents of a continuous model that actually then represents the cosmic web. As the agents move around, they generate a density field. You can think about the density field as a three-dimensional histogram of these agents, of these particles moving around in space. So again, as you know, in the previous part, we're going to work with a three-dimensional scalar field where every cell in the 3D space, in the 3D grid, stores a positive real number. So by now this thing has converged and we have a structure we can look at. The visualization in this can render the volume directly. So it's you basically just show the density of the volume mapped onto color using this transfer function concept, and we are going from blue to sort of yellow in the density. There's different visualization modes that can highlight just a certain segment of the density field. So for instance, here these kind of golden blobs, they represent the galaxies and their sort of circumgalactic neighborhood. And then the purple visualization on top of that is the actual cosmic web estimate. Again, here the colors are chosen so you can distinguish between those two. So that when you do stuff like slicing, you can zoom in and then see the individual galaxies and how the cosmic web estimate actually aligns with them. You can use different coloring methods to segment the density into several different brackets, let's say. So you have blue for low density, green for sort of an intermediate density, and then red for coarse of the filaments. Again, I can play with the parameters and actually get something out of it. I can control the transfer function, so the coloring in real time, so I can change the proportion of these different parts. But the most important or interesting thing for us is going to be this mode. So the way how all this happened is that we were developing these different modalities to show specific things. Tomorrow I'll talk more about what those things are and how we sort of decided on these visualization modes for what they are. But for today, we'll just use this visualization mode, which is the actual implementation of volumetric path tracing. So I haven't explained path tracing yet. Who of you knows who have you ever heard path tracing? Okay, some. So I showed you photon mapping, and photon mapping is the easier way to think about light transport, because you can tell I've been rendering clouds for most of my life. So if you have a light source, it shoots photons into the volume, and then you don't care about the individual photons, but you care about their density, right? Their distribution. So there will be more photons here, and as you go in, they get sparser and sparser. When looking at clouds, you can see this, wherever the sun is coming from, you will have the brightest part, and then slowly that will diminish. But of course, it is also a local function or local behavior, so that if you have a little, cauliflower puffs of water vapor, they'll be visible because of sort of neighboring parts of the cloud of what is inside. So light transports beautiful in the sense that things interact together globally, but also locally, and so the actual appearance will be a function of both of those things and how they interface with each other. And again, our brains know how to understand it. So anyway, so photon mapping is kind of the forward side of simulating things, but it's quite impractical. If you remember, I told you that you have to store these photons. It becomes a huge data structure that you have to navigate and represent. So we don't want that, and so that's why people develop path tracing as a sort of quicker, easier way of doing it. So let's say we have our volume. Can actually everyone see this? Or do we have lights? Yeah, you can see this? Okay. But yeah, maybe. Thanks. Thank you. So, okay, here's what path tracing does. The camera. On the camera, we have little pixels. For every pixel, we shoot a ray or a path into the scene. And the moment we hit the medium, we start sampling along this path in the search for the first interaction with the volume. Okay, so because this is a probabilistic process, we don't know where this will happen. We don't know where the point actually lies. But there is algorithms. One of them is called delta tracking. We don't have time to get into that, but happy to chat afterwards. But basically, you sample the transmittance function inside of this volume. And when you hit the first particle that would interact with the light, where you cut this, and then you treat this as a new point of interaction. What does that mean? Well, in the rendering equation, we have if you remember, the transmittance. So that's actually accounted for in this segment, how much the medium sort of removes or interacts with the light or interferes with the light. And then we have the scattering, which happens here. If this is absorption, well, you just stop. So that's boring. But most of the time in any interesting media, you will have a scattering event. And so you have to continue this path. And so what do? You sample sphere of directions around this point. We did this with the sphere, of course. And you then shoot a new ray in some stochastically chosen direction. And then you just recursively repeat this. So shoot a ray, find an interaction point, sample a new direction. So this is the direction. And again, we will step along this until we find a new interaction point and restart the whole process. So really all that path tracing does is shoot the ray, find find the interaction. And then that's it. To the ray, find the next interaction. And then you just continuously do this until you get out of the volume. If any of these ever is an absorption, which you determine from the proportion of the scattering and the absorption coefficients, well, then you just cut the process and do the new path. But if not, then right here you look for light. So for instance, there can be something in the background, like in the visual reduction setting, you'll have some kind of a skybox, there will be clouds, there will be the sun, there will be whatever, aurora borealis, and that will actually emit light. And then that light will sort of in reverse direction flow along this path that you generate, and you end up in the camera. And all you do in the camera is just you shoot these paths, usually hundreds or thousands of them, and you just add them up. And that's your Monte Carlo estimator of the volumetric light transfer. The reason why we call these paths is because it's a collection of rays or ray segments, right? So here is a ray, the second one, third one, they don't continue to infinity because in finite amount of space or distance, we generate an interaction with the column. But the process is really simple, and this makes this very useful for any practical setting. Because think about it, when you're working with a visualization tool, right? You want to, let's say you want to find a nice viewpoint. I want to show this structure, whatever the structure is. So, you know, you can pass around with matplotlib or something, or you can just kind of find the place that you like. Position, I mean. Slice it up. Zoom in, you get the idea. So what this here is running is a ray marching. So this is fast because at every frame we just shoot a ray for every pixel and then do the ray marching with the emission and absorption model. So what you're seeing here is just emission and absorption. And in the path tracing, where we add these recursive interactions, then we can account for multiple. Can we shut down the light on the back? So I just want to show you what the different interactions that we talked about like.
All right, that's where we started.
Oh yeah. So. Whoa. Can we just shut them off? Yeah, I just wanted to. Okay. I just meant this. Sure, actually. Yeah, just this.
Was nice.
It's very pretty.
Oh, it's this. Nice.
It's ridiculous.
Awesome, thank you. So I just want to show you what those different interaction types actually look like in the volumetric setting. So the simplest thing that we can show in the volume is just emission, nothing else. And for that, I'm just going to make both absorption and scattering 0. So here is just emission. I can sort of adjust the intensity of that. So you can see this, it's not bad, maybe. You know, it shows something. The problem is there is absolutely no intuition about depth in this. So we have a three-dimensional structure, and yet you don't know what's behind what. And from the model, it's very clear why that is, because when you're marching along this ray, well, you just add up all the emission that you accumulate inside of the volume, right? There's no occlusion. There's nothing that tells you how big things are. That's maybe not a problem if you have a thin slice of this, but when you have this full thing, well, tough luck, you know, what's there? Everything occludes everything. So this is not very useful, I would say. And so the simple thing that you can do to actually make this better is just add absorption. So absorption is ambiguous distance because the furthest things are, well, the dimmer they will be. So if you have a volume which is full of these structures which are, you know, similar to each other, then you can tell them apart at least by occlusion. And so if I just crank up the absorption in this, you see that first everything becomes dimmer. So I can compensate for it by just increasing the exposure. So kind of like in a camera. And now you see that things are actually occluded by each other, right? Does it make sense? So, yeah, here we have actually two transfer functions. One is for galaxies and one is for the filaments. So if I crank up the intensity of the galaxies, then they become brighter. I can also crank up the one emitted by the filaments, then they become brighter. But yeah, especially when you have the luxury of rotating this thing, which we sort of see interactively. Actually, what is it? So yeah, but the real magic work. So this is ray marching again, emission and absorption, and then when we want to add scattering into it, we actually have to do the full transport using path tracing. And so what this implements is a volumetric path tracer, where at every frame you shoot a single path for every pixel, and then you add that sample into the existing buffer that's already sitting there. And so what you get is, if you change the view, the whole thing is going to be very noisy for a little bit. But the moment you stop moving it, it starts converging to the ground. And so, because this is a GPU implemented path tracer, it runs 30 milliseconds per frame. So in a single second, you can generate 30 samples for every pixel. Usually hundreds is a decent number to have a nicely smooth converged image. So what you have in this is a tool where you can still interact with the visualization pretty decently. Still, every frame you see what's happening, at least in here on the screen, on the projector, not so much, but after the session, we can huddle up here and see the real thing. And then, yeah, if you're happy with the viewpoint, well, just stop moving it and in 10 seconds generate convert visualization that you can put in a paper. Now, this is a parameter that's important for determining the overall brightness, but also the proportion of light that's absorbed and scattered. That's whoever heard the word albedo. Albedo, okay, nice. So yeah, graphics people also use the word albedo for saying exactly the same thing. What's the proportion of light that gets reflected or scattered in an interaction? So is the ratio between the scattering and absorption. And so what we can do here is set a very low albedo, which will give us mostly an absorbing medium, which also emits, or set the albedo very high, which will give us a very bright medium that also emits. It's so bright we can't see anything. So when we decrease the exposure, we actually get the structure. And so what you see here is something that glows a lot and scatters a lot, doesn't absorb as much. So this might look interesting, but you don't see all that much structure. There is something called scattering anisotropy, which is the degree of forwardness of the scattering. So basically, my bottom here is a particle of the medium. How much of that will go in the forward directions versus sideways or even backwards. And so what I skipped in the previous deck of slides is usually model it by a single function, like a ellipsoid distribution, or you can think about a spherical Gaussian. In one limit, this is a Dirac distribution that's perfectly forward. In the other limit, this is an isotropic distribution. And basically, you're just navigating this by navigating this single anisotropic parameter. So right now I have it set up roughly in the middle. If I make this completely isotropic, well, I just made an isotropic medium, so things look kind of more diffuse. If I move to the other side of the spectrum, you see that everything becomes much more kind of pointy and defined, sharper, if you will. Yeah, so this is usually what I navigate or change. Visualization, usually high albedo is not so great because yeah, it just makes much of the structure vanish. So usually somewhere halfway is a better choice. Wow, this is very slow. Okay, so far so good. So I can also do slicing in this mode. And this cuts out a section of the medium. Here you can do things like trying to create an artificial perspective using scattering as a device to distinguish between different depths. So for instance, I can flood the scene with a fake additional medium that's just everywhere and it has a constant density. Yeah, so it becomes kind of an additional scattering and absorption device or thing. And in this case, playing with the anisotropy and with the albedo, I can actually get different kind of, I don't know how to call it, just behavior with distance.
For your exposure parameter, is that changing the physics or like the brightness? Whatever, or is it just for the visual?
Just for the visual purpose.
All the other things are changing.
Yes, yes. It's really like an exposure on the camera. Yeah, so the good thing is exposure is independent of the transport, so I can change it in real time without having to restart the entire simulation.
Are there other parameters? So I'm assuming that then will be like depending on the exposure, you might see things that you might miss. With other exposures. Are there other parameters that have this?
You mean similar purpose, like to make things visible or?
Yeah, I guess I'm thinking, I see it, I mean, this is really cool, and I've seen it as like, oh, cool, if exposure is -1, you might miss something. So you might see something that you missed when exposure was 0 or whatever.
Yeah.
Are there other parameters that either you have or you've thought about considering?
I mean, to some extent, all of the transport related parameters, they can emphasize things or make them sort of subdued.
Yeah.
Yeah, I mean, as I play with these values, you can see the structures kind of they don't pop in and out, but they change in proportionality, right? If I now crank up the albedo to be almost 1, everything just brightens up, but it doesn't brighten up equally throughout the entire domain. Because if I were to decrease the albedo now, things that are further would darken up more because the absorption from the greater depth. Yeah, so you can actually emphasize different regions of the volume differently as well.
So that allows you to, oh, now I can see more structure close to that.
Yeah.
Okay, I guess I was thinking of like, I guess both can be true, like that is also changing physics, or what, you know, what is physically there, while also giving you more to see.
Yeah, I mean, the exposure, like the exposure matters a lot when you have a scene with a huge dynamic range, right? Like if you have a landscape and then the sun, of course, the sun is like a million times brighter than anything else. So there you might really miss features you overexpose or under. In here, you know, it's up to you to distribute the intensity, so we don't have such a high dynamic range. So usually it's just about finding the right exposure bracket. But yeah, here just by playing with the proportion of scattering and absorption, we created a way to show depth of things. So even though, you know, this is a single volume, there's nothing that's more or less intense, just the fact that these parts are deeper in regard to the camera, makes them more blurry, also dimmer. We actually created color gradient just by playing with scattering and absorption. Yeah, I can sort of create a different multiplier for the density of the filaments. Wow, this is taking further. So I can make the filaments less chunky, or I don't know how to call it, like less pronounced. And then we can see further. So if I increase the slice we are seeing, you get this kind of, I know, stuff disappearing in distance. Come on, Zoom. Yeah, so this is not a great visualization in the sense that you can't really distinguish things, but you know, it might be a nice picture for a cover of something, or a popular science article you're writing about, you know, for general population, for people who actually don't have an idea about the technical best. Yeah, some of these parameters, they are just kind of technical variables for the path tracer, so they're not super interesting for us. So here's a sort of half scattering medium, let me just zoom out. So here is a Hall scattering medium with some density. I've chosen now, the density is 1. If I increase it to, let's say, if I double it, it just becomes much darker because now there's a lot more absorption happening between the data and the camera. But we have also this ambient medium on. So if I turn that off, we only see the data and things become dark. Can play with the anisotropy. So yeah, so when you see an image like this, I mean, there is a lot going on. But what can you distinguish then? You can see the galaxies right there, the bright spots. What is exactly? You see that there's nothing. It's empty region of space. Connectivity. You see that the galaxies are actually inside of the filaments, right? They're never just kind of open randomly. They're lack of data around it. But mostly the core, they're always in the region. Okay. And then there's the color work. So the palettes or the sort of transfer functions I've chosen for these are the hot one, like the black body radiation one from galaxies, and then the sunset transfer function for the film. There's actually 2 different transfer functions applied in the and for instance, the filaments, you can see that they don't move flow, but they never turn red. And so the galaxies, they always flow sort of red to white, and so they naturally transition from white in the galaxy cores towards the outskirts, which turn red, and then yellow. Yeah, looks much better on the screen because yeah, the colors are not watched by the projector, but so this is the kind of somebody was asking a question in the last session, like how do you choose the colors? So it's about experimenting with these things. It's not like there is any fundamental reason why they should be like that, but it allows you to distinguish between different parts of the data set and to show them, comment on them. It's a different one. So, so far this was a data set of galaxies, 30,000 galaxies or so. This is the Bolshoi-Planck simulation, I think 13 million halos. So it's just a lot of red points in this mode. But yeah, we still have so the reconstruction is still going, and the filaments are kind of green now. Yeah, this takes a while to converge, like a minute. But let's stop it right here and see what path tracing can do for us. So yeah, when you look at this thing, it's just a big chunk of filaments, you know, messy stuff. So what can I communicate through a visualization of a quantity of data like this? Well, definitely slicing or trimming the volume is a good thing because we know that this structure should be more or less the same everywhere, so we don't have to show the whole thing at once. So I just kind of slice it laterally. Then here we have a part of it. So we already see filaments. They're not completed because I didn't let the reconstruction finish, but you know, it's good enough for now. So it's the filaments, we see the voids, see the galaxies. Sort of, I can change the proportion of them, so we have more optical density to the galaxies. And then again, using the tools that we already discussed, you know, absorption, albedo, proportion between scattering and absorption, I can achieve an effect where sort of the voids become kind of fuzzier. Can you actually see that? So we actually paradoxically decrease the contrast of the voids because we added this ambient medium which lightens up everything, even the voids. But now we see that voids are actually also part of the volume, so we can sort of direct attention to that. So right here we have a large void which is kind of well, it's flooded with this ambient medium, and so we see that fuzzy atmosphere to it. And make everything denser. And yeah, again here, the example of changing the albedo. So if the albedo is very high, everything glows like crazy. The effect of things that are deeper or further from the camera actually gets stronger because all the voids get fuzzier. But then I can decrease the albedo. And the sort of blurry diffusion is gone and everything becomes sharper. So generally light scattering is kind of a low pass filter on the light distribution. So the more scattering you have, the fuzzier things become. So if you want to show something sharp, like these structures, which are these things, filaments, it's better to have low albedo, so higher absorption than scattering. But if you want a nice atmospheric picture with the depth of field, then more scattering is actually better. Also changing the anisotropy of scattering has similar effect. Oh.
So I thought the purpose of trying to create models like this, we're trying to get something that represents the however, I think changing these properties doesn't get the image, then like going against that idea of what is
Right. Well, that's a good question. So I guess there are two kind of contradicting tools or pressures here. The one is to show the data, and the other one is to show something that's intuitively understood. So the argument was that we humans have intuition about physics of light transport because we look at volumetric lighting all the time. So if you use light transport, physically based volume rendering as a device to visualize data, as long as your math is correct, this is going to be a representation of something that you could realistically observe if you had a medium that actually has these parameters in real life, right? And so your intuition about this is going to be better than if you just do a random visualization based on whatever assignment of color. So the physics helps you kind of carry out that intuition. On the other hand, you also need to show the data and show as much of it as clearly as possible. So here we are playing with sharpness of things because let's say we want to distinguish filaments. In this work we've done, we also want to show how the galaxies align with the intergalactic medium. Like, is it well connected structure? Do we reproduce the voids, right? Or are they there at all? And so to show that, yeah, you have to massage the data a little bit. And because there is no right or wrong, well, you can make whatever assignment you want, as long as you don't make claims like, this is what the universe looks like. I mean, it's not, right? It's definitely a false color image where the false color process is taken to the next step of including light transport. But it's not lying with data, it's just there are these structures we want to distinguish them. But yeah, it's tricky. I mean, people come up to me and say like, yeah, images, it's like do whatever. Well, yeah, there's visualization. It's not like if we were ever limited only to things which can exist in real life as a physical medium, well, we would be 3D printing them, right? That would take a while, but it's a valid visualization method. So here we have the luxury of setting things. We want to color them as we want, and we don't pay those time.
Question that kind of connects the two or tries to bridge the gap, because I understand that we're exploiting the human ability to visualize things from that, but maybe it's just because I'm not used to papers that have a ton of these, but translating it to like histograms or something that I can put on a plot. Let's say the biggest, like the distribution of voids, the distribution of places where 90% of the light is dark. Seems like playing around with those visually, you can modify that. So how do you translate something like this that's very visual, something that's like super boring, just purely numeric?
Well, you do both.
Right.
Yeah, I mean, there is no way around it. Like, this will never replace rigorous statistics.
Right.
I mean, our visual system is horrible in judging proportions of things, right? Like, if I asked you, well, what's the volume of the void here? Like, you might give me a ballpark estimate, but only statistically you can decide that. But you can gear the visualization towards actually showing you the statistics. You can come up with the coloring for voids and for non-voids, and then just count the pixels. The trade-off here is, of course, that in a rigorous statistical plotting, well, if you plot a histogram of these quantities, how many numbers can you realistically put on a plot? Like 1,000? Like, let's say a histogram of this density. I have a little histogram feature right here. You can see down there. It's like it's very coarse, like 12 value histogram. But you can't do more than 1,000. It just, even if it's a continuous line, like it has limited number of pixels, let's say, or in a print limited number of ink dots that you can put on paper. This reconstruction of the cosmic web here is like a gigavoxel, it's a billion voxels, right? So we're literally putting a billion values on the screen simultaneously. And That's a plot that of course will have a huge loss of information. That's like, it's a trivial statement because even just the number of pixels on the screen is 1,000th of the number of voxels. So there's a huge reduction of the bandwidth that you can set to filter. The question is then, well, how to do this reduction the best, right? And again, the argument, well, use physical intuition feels like a good one.
I'm just gonna add, right, like you need frequently higher order statistics. Like to explain this, right, and your intuition statistics gets heavily worse.
Yeah.
Higher and higher orders, right, so. Kinds of, even if there's some loss in your rendering choices, better intuition will image, and you'll ever get by bringing 5-point correlated function or 100-point correlated. It's
Yeah.
I think it's an interesting problem. Data compression. City trend.
Yeah, this is a great discussion, because I mean, there was a point in time when we didn't know of cosmic web, right? Like before 2005, we had no visualization of this. Before the 70s, we had no mathematical framework to think of cosmic web, even as like high order statistical entities. So at some point there was time when people didn't even know how to ask these questions. Like, oh, how many voids are there? What? What's a void? Like, we first had to define those things, and we define them intuitively, right? Well, voids is a big old hunk of empty space, and or less empty. Seeing that empty space helps us define those terms in first place, and then we can iterate on it. We can decide, well, where is the boundary of voids? So yeah, visualization can deceive people. Right? You can show something and then convince them, oh yeah, that's what it looks like. Then you intuitively think about it in those terms from then onwards. Which is why I don't just create these for my own pleasure, but I work with an astronomer or astrophysicist who actually knows, I mean, hopefully. We're talking about it. Like, yeah, this is meant to be a proxy of the dark matter distribution. I mean, what does dark matter look like? Well, it doesn't even interact with light. So we can invent virtual light that interacts with virtual dark matter, show what it looks like, and then be like, well, can it even exist? And yeah, statistics have to come on it. Okay, so
So is it right to think of this as more of a exploratory tool and a like communication tool rather than like strictly analysis tool? Or
Yeah.
something? Okay.
Absolutely, yeah. I mean, in the papers we wrote about this being applied to the cosmic web, like all of the figures are this, all of the figures are actual rigor response. And you know, they should talk to each other, ideally. Yeah, I'll show you some tomorrow. So okay, so this was, we were like halfway through, right? Half time. So this was to hopefully support the theory from the first lecture, to build intuition about what these parameters look like in visualizations, to also to sort of hopefully convince you that interactivity is a good thing. I mean, again, you got this stop motion version of the interactivity. So I encourage you after the session, please come up here, play with the visualization, rotate with it, zoom into it. It's much better when it's 60 frames per second than 0.5 frames per second. Because I mean, what we didn't talk about is parallax, for instance, right? We have stereo vision. We can see things in 3D without necessarily having a 3D. Okay, whatever. You get the idea. Parallax is important. So when you rotate things, even on a single display, you can see things 3D just by wiggling the camera a little bit. Right? You can't do that in a plot. So the thing, okay. Small break. I just want to test your intuition building skills. Here is a visualization that shows whatever, that shows something that's absolutely unrelated to the universe or astrophysics, but rendered with the same tool and reconstructed with the same tool. And this is a stereoscopic pair. So those of you who can cross your eyes, so change the versions of your eyes, sort of look at the tip of your nose kind of thing, you might be able to see this in 3D. Unlikely that people on the sort of sides of the room will be able to see it because you need to be roughly in the center.
You want to get up and go to the, that's fine.
Yeah. So try to do,
Doesn't work.
yeah,
Oh, got it, okay, like.
yeah, just try to do like,
Trying to make us all.
yeah, the finger trick is good. Like try to look at your finger, put it in the right distance, merge these two together. You will see three images. One of them is left and right, that's mono, and then the middle one will be stereo.
Yeah.
It's so hard.
Yeah.
I see the three, but I can't.
Yeah, it's hard. You also have it harder because you're close to it.
Oh.
So actually, right under the clock, I think the
Oh, that's sick.
yeah. What?
You see that?
And then you see like a 3D.
This one,
It's hard. I'm tempted to like see you, right? Like trick my finger. Weird. The negative space is like an image appears like on top of your finger.
Den er tur.
Like change. But you need your.
Somebody speaking through Zoom.
Face.
It's distracting.
Maybe a voice.
Right, so a little quick distraction. By the way, this thing with versions, like looking at your finger and changing versions and changing focus, good exercise for your eye muscles. So after those long night sessions, staring at the screen, just 30 seconds of this, that actually like decreases your eyes fatigue and also long-term impact of staring at the screen. Yeah, you might save yourself a pair of glasses. If I knew it, 20 years ago. Cool. Oh yeah. Oh. So second part today is 2 exercises. So first of them, we'll use a tool called Cosmovis. This is a volumetric render that actually runs on the web, so you don't have to run a C++ craziness like now. Is it still running actually? Okay. So Cosmovis is a tool that we were developing in the team of these people down here. David is the first author of this, and it runs on the web. It's a volume render that will run on any machine. So this is where you find it. So those of you who have a computer, please load it up. And those of you who don't have a computer, just join. Okay, I don't think there's a single solution. Cool.
Is also on Slack, if you don't want to type everything out. Oh. Just click it there.
Thank you.
I used to do that. Yeah,
Oh,
yeah,
okay.
yeah. It was-
Well, then I don't know how you do it.
Yeah.
I get it.
As like helper too. Yeah, it was like, that's probably why, but so.
Reason I didn't know.
Just nothing going on, yeah.
You know what DF is?
Like going into.
Like, so I can do.
Hey, like looking around.
Oh,
Oh.
Okay.
Finger scroll.
black hole.
Have you loaded? Oh, hey.
No, like a, like a. It's just the.
Looks like.
I don't know, I'm live.
Yeah.
So very quick overview of the interface. So by the way, this is a volume visualization tool, just like the one we've been looking at, except there is no path tracing, so no scattering. So this is just emission and absorption. The interface, data selection, which box, you can sort of slice it. You know, this should be pretty obvious. See that? There is layers. You can switch off, you know, gas. There is star particles, which are really like macroscopic star particles. You can turn on dark matter. This this fuzzy cloud overlaid on top of regular gas distribution. There is stars. You can change the size of the particles. And then some filters for galaxies. We don't have to do that. There's also skewering, so you can do a virtual spectroscopy measurement on this data. So you just rotate this, click on skewer mode, click into the volume, and then you generated a skewer in the direction in which the camera was looking. And then this actually is going to give you a linear spectroscopic measurement of absorption. So when you click on request skewer distribution, no wait, which one is it? They might take a while. Where is the server? Anyway,
Stress tangents.
I think I shouldn't have clicked request skewer data, but just request the skewer.
Right.
Is it possible that everyone being on it at once is?
Yeah, I think so. Yeah, this runs on Kubernetes, I think, and yeah, it's just.
We can solve that.
Yeah, okay.
Sitting with a partner. Or with said partner. It's gonna factor production. The server, so.
Oh, no. Yeah.
You are.
I love it too for now.
I'm Raina.
The first one, right?
Okay. So anyway, so the
Okay, I'm 6.
the exercise is to actually do little storyboarding. So using the Cosmovis as a visualization tool, try to make a 3-panel figure where you kind of tell a little story with the data. And the story can be whatever you want. The data is limited to what's already loaded and pre-processed in the software. But it can involve, slicing, different transfer functions, so different ways of coloring the data, showing dark matter versus regular gas versus the stars. Really anything you want to tell, and it doesn't have to be too difficult. It's more just working with these affordances. Yeah, to just composite the figure together, you can use a tool called Inkscape if you know what it is, or any drawing tool that you work with regularly, like GIMP or whatever. Yeah, it's just image manipulation tool to composite the figure together.
Like,
No, I don't have.
I think
You,
it's just.
Oh, yeah.
Maybe.